Okay, everybody. Welcome to this session on cybersecurity and threat hunting. I'm very excited to introduce our speaker for today, Sneha Banerjee. Sneha is a cyber threat hunt analyst at Microsoft, where she hunts and removes advanced threats in Azure infrastructure. She has extensive experience and skills in cybersecurity domains, such as penetration testing, risk management, cryptography, cyber forensics, system fundamentals, and security auditing. She has also worked on machine learning models, incident workflow patterns, and advanced threat analytics for various organizations. Sneha is not only a proficient hacker, but also a passionate mentor and leader. She has mentored several cybersecurity aspirants and promoted diversity and inclusion in cybersecurity, which has led to many awards and recognitions. Sneha is here to share her insights and expertise on cybersecurity and threat hunting with us. Please join me in welcoming Sneha Banerjee.
Thank you, everybody. A very good afternoon, ladies, gentlemen, and all the fellow cybersecurity enthusiasts. I'm so honored to be standing before you. I want to express my heartfelt gratitude to Hackfest for inviting me over here. So I'm honored to be able to bridge the digital divide from India to Canada to delve into the realm of cyber investigation that remains one of the most powerful and cutting-edge tools in our arsenal when it comes to investigation, and that is RAM forensics. So before we begin, just a little bit about myself. My name is Sneha Banerjee, and I work as a cyber threat hunt analyst too at Microsoft within their cloud and AI global threat hunting team. So my journey in cybersecurity has been fueled by a passion for constant learning and making a commitment to make this digital world a safer place. So in terms of qualifications, I hold several certifications, including the GIAC Certified Incident Handler, Certified Ethical Hacker, Certified Azure Red Team Professional, and AWS Certified Solutions Architect. So talking a little bit about my educational background, I hold a bachelor's degree in computer science and engineering, and I also wanted to dabble a little bit in data science and machine learning, so I've received a professional training in the same at IIT Kanpur. But beyond my qualification, what truly motivates me is opportunities like these where I'm able to mentor and share my knowledge to the next generation of cybersecurity enthusiasts. I take utmost pride when it comes to helping people develop their skills in cybersecurity in a manner where, be it providing technical guidance or if I'm offering any sort of career advice. Additionally, I'm also very deeply committed when it comes to promoting diversity and inclusion within the cybersecurity community. And I'm humbled to have received several awards, such as the Cybersecurity Woman Influencer of the Year by B-Sides, and being nominated by the SANS Difference Maker Award. So it's my belief that sharing knowledge is something that I'm very passionate about, and this can collectively help us strengthen the cybersecurity landscape. So today I'm very excited to share my insights on exploring RAM forensics for effective digital investigations. So before we begin, a quick disclaimer that whatever information, the presentation that I share in front of you, it's a product of my own personal views, insights, and experiences, and does not represent the official stance of Microsoft, where I work. So talking about today's agenda is going to be a deep dive into the world of memory forensics, which is a powerful tool for effective digital investigations. So we are going to explore a whole lot of key topics which will help us to understand and leverage memory forensics within investigations. So firstly, we're going to talk about the introduction to memory forensics. So we'll outline the importance and what relevance does it hold in cybersecurity. Then I'm going to be talking about Windows memory analysis, where I'm going to highlight these specifics of how to analyze memory when it comes to understanding Windows environments, and maybe talk a little bit about the essential concepts and techniques. After that, I'm going to talk about some memory data structures. So we are going to be exploring some critical memory data structures like eProcess, PEB, Process Environment Block, LDR, and VAD tree. And then we will introduce to volatility, which is a powerful open source tool when it comes to doing memory analysis. I'm sure some of you might be knowing about it, and explain that how it can be an invaluable asset when it comes to investigations. And then we are going to talk about some of the four steps as to how you can locate the initial catch. So it's like finding the initial point of compromise in a system's memory. So the way we are going to do that is talk through 4 different steps. So firstly, we identify the rogue processes. Then we analyze the process DLLs and handles. Then we review some of the network artifacts in memory. And then finally, we are going to look for some of the evidence within code, evidence of code injection within the RAM data. So let's dive into the fascinating world of memory forensics, shall we? So this is a crucial aspect of digital investigation, which provides a valuable insight about the system's activities. So memory forensics, as I'd like to believe, is it's all about acquiring, contextualizing, and analyzing it. So ideally, when I talk about RAM forensics, I consider that this analysis includes both the physical memory from the RAM and also the data that's coming in from the page file, which is also known as the swap space. So here's a breakdown of the 3 steps. That is, first we acquire. So this step involves acquiring the RAM memory content of the target system. So ideally, throughout the presentation, I have captured raw memory using WinPmem. So next comes the context, like how do we establish context? So once we have acquired the memory data, the next step is to establish context, and by that what I mean is by understanding the environment where the RAM data has been captured. And then we are going to be learning about the specific memory offsets, which is relevant to our investigations. And then we are going to analyze, where we are going to be analyzing for some of the significant elements. Like this could include things like processes, network activity, open files, etc. It's all about finding the needles within the haystack. And then finally, we are going to recover evidence. Like so ultimate goal as a cyber investigator is to recover the evidence that can be used for digital investigations. So this is the approach that I'm going to be taking throughout the presentation. So firstly, we identify the context. So we find something known as the kernel debugger data block. So this block serves as the starting point for accessing the vital kernel data structures, right? So if you begin by thinking about the KDBG, and then from there on, we move on to understanding eProcess. So eProcess, it represents the active processes that are there within the system. So all the active processes that you see within the system, they all have respective eProcesses in them. So by parsing these structures, we can gain a deep understanding of like how the running processes are, what are their characteristics, and what associated information they have. After that, from eProcess, there is one part, one data structure within eProcess, and that's called the process environment block. Now, these are associated with individual processes. So parsing PEB blocks helps us uncover key details about each process's environment. And then we'll be talking about the DLLs loaded, that is the list of dynamic libraries that provide, that are associated with each process. And then after that, narrowing down, we will then talk about the virtual address descriptor. So virtual address descriptor, or as we know, it is VAD tree. It is crucial for understanding memory behavior. So when we pass the VAD tree, we can identify the memory sections that are allocated to the processes. And then we are going to talk about how do we scan for outliers. So how do we see, like, if there's any unlinked process, if there are any processes that are not linked within the e-process doubly linked list, so that is an indication for an outlier. So we are going to be seeing presence of such outliers in the upcoming slides. Okay, so this, like the way I was trying to read a little bit about memory structure, so I tried to simplify it by using this diagram. So let me begin by just talking about RAM, right? So RAM is a system that takes the task of short-term memory in the computer. So it's usually the main memory or the primary storage in the computer. So it's considered for loading, displaying, routing applications, etc. So whatever, be it files, be it network connection to registry hives, everything is available for analysis within RAM data. So now let me talk a little bit about the structure of the KDBG. So KDBG is a structure which is maintained by Windows kernel for debugging purposes. Right? So it contains a list of the running processes and loaded kernel modules. So within KDBG, there is one data structure which is called the e-process. Now, the pointer to the e-process structure is stored within something known as PS initial system process, which I'm going to show in the subsequent slides. So within e-process, there is another, there is a sub data structure within it, which is known as the process environment block. So PAB contains all the process-related information like the image name, like the loaded modules, the image file path, and the command line parameters that are associated with the running processes, right? So another structure within e-process, apart from a process environment block, comes the active process links. So active process links is like an active entry structure, and it's like a circularly double list. So there's one plugin within Volatility, which is PS list. So it leverages this active process links to see what are the current processes that are running. So I'm going to be explaining that in detail in subsequent slides. Yeah. So having said that, let's try to do a mapping between the volatility plugins and OS data structures. So the reason why I came up, the reason why I'm explaining about memory data structures before actually diving deep into memory analysis is the fact that rather than simply running volatility plugins, it's very important for us to understand that how each of the volatility plugins are actually passing the data structures. So this is like a simplified version of how volatility plugins are mapped against their respective OS data structures. So you can see that majority, in fact, all of the volatility modules have e-process associated, e-process data structure that's associated with it. And then PS list has active process link, which I just said. And most of the other modules, they depend on the PEB, the process environment block data structure. So how does PS list get the current list, get the list of current processes? So like I said, each Windows process is represented by an executive process structure, which is called the e-process. Now, e-process in itself contains many attributes, and it also points to various other data structures. So talking about PEB, which PAB, so it contains things like image name, loaded modules, image file path, command line parameters that are passed within the process. So one of the fields within e-process, which I briefly alluded a while ago, is the active process links. Now, active process links is a pointer to a circular doubly linked list that tracks all of the active modules. So the PS list plugin within Volatility picks up this point from active process links so that it can get the list of all the active processes. So I'm going to just do a deep dive into the e-process data structures using the kernel debugger to exactly show you how it looks like. Yeah. So like I said, like PS active process list, process head is the pointer to the doubly linked list. Now, like, let's not get confused. So active process link is the one that is used to link all the e-process data structures. But if we want to get to the absolute root of things, like now we all know that the system process is the absolute, the very first process that you see running within the system, right? So if you want to get to the topmost, the starting point, so the way you do that is by running a PS active process list. So when you get a pointer to one of the nodes within the doubly linked list, we can then use that to traverse through all the active processes that are connected via the doubly linked list. So I'm going to talk a little bit about the approach taken by PS list. So first step is to get the pointer to the doubly linked list using the PS active process head. And then after that, what we are going to do is we are going to list the instance of the active process links of the process that's being pointed by the pointer itself. And then as you can see over here, this one, the F-link. F-link entry at this pointer, it points to the active process links of the E-process structure of the subsequent processes. So if we want to get to the other element of E-process, we need to first get to the top of E-process. Now, like to simplify things, like E-process has different data structures, right? So if, again, if we want to navigate across other data structures, so we use the offset. But whereas if we want to go to the next data structure, we then first subtract the offset, go to the starting point, and then we subsequently navigate towards other active process links, right? So that is the that is in brief what the thought process is like when PS list is executed. So now we then leverage the list capabilities of the debugger and traverse through the list. So what we do here is we subtract the offset from the pointer to reach the starting point of E process, right? So here what we have done is this is the offset. Offset. So whenever we want to reach to the starting point of E process, we first subtract the offset, and then from there on, we can access any of the data structures within E process. Okay. So this is how we are traversing through the list, and we are able to identify all the current processes that are running within memory. Okay. Now, within E-process, there are other fields and structures like PAB, PB, LDR data table entry, VAD, and etc. So these are the other memory data structures. So I'm going to talk a little bit about the LDR module. LDR module is one of the most trusted plugins within volatility to detect any sort of DLL hiding or injection activities within the memory. Now, we're going to be talking about the process structures in the memory from where plugins like LDR modules and DLL list actually fetch the data, right? So if you can recollect the slide where I showed you the mapping between the volatility plugins and the operating system data structures, you can see that the plugins like LDR module, DLL list, all of them depend on the process environment block structure. So, but again, PAB, like you think about it like a hierarchy, right? E process, then comes PAB, and then within PAB comes the PAB LDR data. Now, this PAB LDR data has pointers to 3 doubly linked list that stores information about the loaded DLLs for the process. So, like I just alluded, now LDR modules again points to 3 lists, which is in-load order module list, in-memory order module list, and in-initialization or module list. So these 3 lists combined will give us a whole overview of the loaded DLLs for a specific process based on their loading methods and also the locations within the memory. Yeah. So this is how LDR module looks like in the background. So you see PAB, within PAB you're able to access LDR, and then LDR in turn points to 3 different lists here. So this is like a logical connectivity between various memory structures, right? So how do we analyze the PAB data structures within the kernel debugging? So firstly, what we have done, what we see here on the slide is that we enumerate all the loaded processes and select a process that we want to conduct further examination. So first, now that after identifying the offset of the process that we want to investigate, then what we would be interested is we want to get the PAB pointer, right? So we want to enumerate the E process structure and then find out the pointer to the PAB structure as well. So that's why the flag that you see Y followed by PAB. And then now we want to enumerate the PAB LDR data. So this contains the 3 linked lists that I just spoke about, right? The 3 linked lists that you see over here. So PAB stores all the information under the LDR field, and then which again points to the 3 doubly linked list, right? So this is how you can traverse through the entire DLL list by following the pointers to the linked list, right? So same way we can traverse through the other 2 lists as well, like the other 2 linked lists that I just told you. So we need to factor in the offset, like the offset that I highlighted over here. You always need to subtract the offset from the offset of the process in order to get to the starting point of the E process, and then you can subsequently get a list of all the DLLs. Okay, so next comes the other important data structure, which is virtual address descriptors. Now, what are VADs in the first place? So VADs are also known virtual address descriptors. So they describe the ranges of virtual memory space that is reserved for a specific process. Now, I'd like you to visualize VAD as a tree, which you might like encounter in nature, right? So you have a VAD root, and then root again in turn has got nodes and leaves, which are also known as VAD nodes. So together with the VAD root and the VAD node, it contains all the information that is related to the memory ranges, which is reserved for a specific process. Now, how do VADs work? Now imagine like there's a chunk of virtual memory allocations within a process, right? So now these nodes, which are, they serve as the building blocks to map out the virtual memory for each process. So now let's say that if there's a file which is mapped to any of these memory regions, the VAD node would contain the full path information of the file, right? So I would like to think of VADs as the blueprints of a process's virtual memory space. So any memory map files, any information related to that can be found within VADs. So this is the visualization of the VAD tree. So the like I said, it's a hierarchical data structure which maps the operating system's usage of operating system to manage the allocation of the virtual memory space within a process, right? So how does the tree work once again? So each VAD node that you see over here, it represents a chunk of continuous virtual memory address that's allocated to a process. Now these chunks can be small or they can be large. Now these nodes, they not only indicate the memory region that is within use, but it also contains some very critical information such as memory ranges, protection flags, and most importantly, if there's any file which is mapped within this memory region. So let's say that if there is any file which is mapped within the memory region, which is within the VAD node, it can contain full path information. So we can use VAD node if we want to identify any sort of DLL injection activities. Now sometimes what happens is if any process is unlinked from the E process data structure. So chances are you may not find them in PS list, but you will definitely find them in the VAD node data structure. So this is why this is very important. Right. So this is what I have done. This is the reverse use the kernel debugger to understand more about the VAD root. So this is the same thing. What I've done is that you just take the offset, you take the offset of the process, and then you try to parse for the VAD root, right? So this, you can see that the VAD root is RTL AVL tree data structure, right? So now why does this matter? This matters because the kernel memory structures and the VAD tree is pivotal in memory forensics. So it enables us to extract and analyze a process's virtual memory layout and understand like what are the different files that are being associated with a specific memory region. Right. So let's delve deeper into the relationship between the kernel memory structures and the VAD tree. Now, like I said, VAD root is the pivotal entry point, and now let's like piece everything together to visualize the broader picture. So VAD root is part of the RTL AVL tree structure, which is kind of a balanced binary search tree. So VAD root, so once you get hold of the VAD root, it will give you access to the VAD tree. Now the RTL AVL tree data structure, which is associated with a VAD root, it efficiently organizes the VAD tree within the kernel memory. So it's the backbone of how Windows manages memory allocations. So if we take a closer look at the RTL AVL tree structure, we find that there is a pointer to the first node within the tree. Right? So this one you see over here is the first node within the VAD tree, and that is a balanced node data structure. So as shown in the figure, you can see that the data structure at this address is of type RTL balanced node, which is a structure that holds information about all the nodes within the AVL tree. Right? So moving on. Now let's talk about the VAD tags. So now that we have understood about VAD root, VAD tree and everything, so what is a tag here? So tags are a critical marker that provides insight into the structure and characteristics of the VAD node that is within the VAD tree. Now these tags are essentially located just before the VAD tree begins, and they act as a label or an identification marker. So to access this access this tag, so we need to look at the first 12 bytes before the start of the actual node. So this tag information can vary from one VAD tree to another, and it may include some very important details such, about the memory range, the allocation type, and other attributes that are pertinent to the VAD node. Okay. So now that we have understood about VAD root, VAD tree, and things like that, so how do we get access to the files that are associated with the allocated memory range? So there is something known as VAD nodes, right? So the way we access it is that it contains information about the internals, that what are the specific files that are associated within a memory structure, right? So by enumerating these MMAD nodes, we can actually get insights like what files are part of it. Okay, so now that we are coming to the main point, is where we are actually getting to the file part. So what we do is that we need to understand the subsection field. Now the subsection field within the VAD node, it holds the key information. That is like what files are mapped within the virtual memory. So by enumerating the subsection field, we are able to get to the, like if I have to think of an analogy, you can think of it like an index of a book, right? So it guides us to specific chapters within a book. So in this case, the chapters are the memory regions, and the index is the subsection field that helps us to find the associated files. So then comes the control area. So as we keep progressing, the control area is where we get to the final point, which holds the crucial element of the file pointer, right? So there is a tweak to this. Now this file pointer you see over here, which is highlighted, it is an EX fast-ref data structure. It's not directly a file pointer, which means that we can't directly get to the file just yet. So what we have, what I've done is like I've gone through several articles and things like that to understand what to do. So the way we have to do that is if we replace this final bit over here, 7b. So if you replace the final bit with 0, that is the offset which will link us to the file within the memory structure. Okay. So having understood some of the core memory structures, let's now understand about volatility. I'm sure most of you must be knowing about it. It's a powerful framework which is used to dissect memory dumps from Windows, Linux, and Mac systems. So the way you curate a volatility volatility plugin is you first describe the platform, the class, and followed by the plugin name. And one important thing which I feel personally is that it's easy to get live investigation kind of results. So sometimes what happens is when you are within an investigation, and if you identify a specific system that has been compromised, so what we do is we typically contain it, we typically remove all the cables out of it and make sure it's not accessible to the internet. But then how long are you going to keep it? Like let's say if it's a very critical system that we can't keep it on hold for a very long time. So I feel that the most efficient way to do that is to get a memory capture of it, so that you get the memory capture, you get live investigation kind of details, and also you don't have to keep the system on hold for a long time. And that's the reason why we as threat hunters and investigators harp on RAM forensics. So how to use volatility? Very simple. You use the keyword, and then -q is to make sure that everything is quiet. You don't get all the annoying messages while the tool is loading. And then you mention the structure of the plugin, which I just explained. So if you want to get image identification, like if you want to understand what sort of an image that you're dealing with, what sort of a RAM data you're dealing with, so you use the image info. So it recovers any metadata from the memory image. And I feel that this is very important to understand what kind of image you're dealing with, is because what happens is sometimes if you are running plugins like PSList, PS3, etc., and if you're not mentioning the correct image type, then chances are that you may be getting some obscure results out of it. You may not get the perfect result. So that's why it's important to first understand what kind of raw data that you're dealing with. So this is like a screen grab of when I was trying to understand the image info of the raw dump that I took. And then comes the volatility profile. So volatility profile it gives you a good profiling of what exactly the memory image is like, right? So and then comes the image copy. Now what is image copy is if you want to understand the hibernation files. Now hibernation files cannot be used directly. So you have to uncompress them first and then convert those crash dump files into raw images. And the way you do that is by using the image copy plugin. Okay. So this 4-step that you see is ultimately how SANS tells us to how to identify the initial starting point when it comes to investigation. So first we have to identify the rogue processes. Now rogue processes are often the starting point of malicious activities. Now these could be things like unauthorized programs or services that are running within the system. So you first identify any rogue process. And then you analyze the process DLLs and handles. So you see that what are the DLLs that are loaded by the process in the second step. And the third step is you review the network artifacts. You see if there's any malicious network connection being made by the process. And then the fourth step is you look for evidence of code injection and see if there's any technique that you're able to detect while you're trying to analyze the processes. So this is the fourth step as how we threat hunters use in order to find the initial catch. So step one is to identify the rogue process. So how do you identify if a process is malicious or not? So firstly, you see whether the process name looks legitimate or not, if it's spelled correctly. It's obvious, right? You see the image name and see if it looks legitimate or not. And then you see the full path. You see that from where is the executable being executed. So if you see that it's being executed from a temp directory or a user's directory, then chances are it's not a legitimate process that's being executed. So likewise, if it's system32, then you know that, yeah, this is an authorized process that's being running. And then comes the parent process. You see, is the parent process what you would typically expect or not? And then you look at the command line, like what command line is being executed, what are the different arguments being executed, and then you look at the start time. You see whether if the process was started around the same time as the boot time or not. If it's very different, if it's not near to the boot time, then definitely chances are that it was spawned by a malicious process and it's not a legitimate one. Then you look at the security ID. You see that the security ID, who started the process, whether it's that of a system or if it's that of a user, right? So this is how I would like to visualize how the processes look like internally. So each process has got its own F-link and B-link, and that's how the processes are interlinked together. And then each process again has got its process ID, parent PID, offset, time created, etc. Okay, so how do we identify rogue processes, right? So these are the four plugins which I keep in handy, and I'm sure most of you would after this presentation, is pslist, pscan, pstree, malfind. So these are the four plugins that you would use to identify the rogue processes. So pslist, like I said earlier, is it uses, it sees all the processes that are running within E process. And then pscan, it scans the physical memory for the E process pool allocation. Now, one key difference between pscan versus pslist is in case if there is any process that is unlinked from E process, you'll be able to see that within pscan. Now, pstree is used to print the process list as a tree, which shows the parent relationship using the E process linked list. And malfind, which I particularly find very interesting, it automatically identifies suspicious system and process. You don't have to keep scouting for a bad process by running pslist. So all you have to do is just run malfind. It's going to automatically pick for you the malicious processes. So this is like the output of the pslist that I ran using the memory capture. So I want to say a quick note that the way I've captured this memory file is by using something known as a winpmem. So winpmem is what I've used to reliably capture the data, the RAM data, and using that, I'm doing all my memory analysis here, as you see in the screen grab. And then likewise, this is same thing. This is the pscan output. So like I said, it's especially useful when it comes to identifying hidden and obfuscated processes. And then again, the pstree, the same thing that I just said. So if you want to see any malicious parent file, a parent process against a process, so the way you can do that is by looking at pstree. And this is the output of the same. So one thing that jumped out of after my analysis is that you see that one node is spawning command.exe. Now this is not something that you would typically expect, right? So one node cannot be spawning a command tree. One node cannot be a legitimate parent process. So this is how you identify rogue processes. And then, like I said, you use malfind to automate the analysis. So you can quickly identify the process that have been compromised without having to go run a pslist. And then step 2 is how to analyze the process DLLs and handles. So these are the different process objects that you typically see that are associated within a process. DLLs, handles. Handles are again in turn pointers to the resources that a process can access, like it can be files, directories, registry, mutexes, events, and etc. Then comes thread, memory sections, and sockets. So I'm sure you all must be knowing it, so I'm just rushing past it for the interest of time. So if you want to analyze the process object plugins, you use these plugins. Keep these plugins handy if you want to know them. So DLL list is to print the list of all the loaded DLLs for each process. Command line is to display the command line arguments for each process. Get SIDs, like I said in the previous slide, if you want to see the SIDs that are associated with process and see if it's a user SID or if it's a system one, so you can do that by running the get SID. Then comes mutant scan and then service scan, right? So this is just the output of the DLL list and the get SID, right? So this is how you can analyze the various process objects. So here you see over here that the command.exe has a user SID, right? So if you see over here, command, and this is a domain user's SID. So this stands out to me because it was not spawned by a system account. So this means that it's a malicious process. Okay, so a primer on what security indicators are. So this is like a list of all the well-known account SIDs. Like these indicate whether it's a local system, local service, or network service. And these are the well-known group SIDs. And then we spoke about handles a while ago, so I'm just skipping past. So if you see over here, you're able to see the process objects that are associated with this particular process. So you see that there's a system certificate registry key that is discovered within one node. So these are some of the interesting handles that you would find when you run when you do process object analysis. And then mutants. Now mutants are process objects which are used by malware to mark the territory. So these make some of the excellent indicators of compromise. So when you reverse process and you find the mutant keywords, it's very easy to identify what process it is, because mutants are something that is typical to only a specific process and can't be replicated to multiple processes. And then service scan. So service scan is to see all the services that are running against a specific process. So if you want to see if there's any stop processes, you can see that by using service scan. And then step 3 is to review the network artifacts. So the way I try to identify whether a network is malicious or not is what I do is I see if there's any process that's communicating over ports 80 or 443 or 8080, and it's not a browser. If it's not a browser and if it's accessing these ports, then that definitely means there's something suspicious. And on the flip side, if browsers are not accessing 443, then again it indicates that it's malicious. And then let's say that the connections to some of the IP addresses that are not associated with any specific business purposes, that also indicates that it's a malicious process. And RDP connections. So if there is any RDP connection that originates from an odd IP address. Now, if some of you may have experimented, you can't RDP within your own IP address. It's not possible. So if you're seeing there is any RDP activity happening within your IP address, then chances are that there's some backdoor has been is doing that, because you can't RDP your own IP address. So these are some of the ways you can identify malicious network artifacts, and you can do that by using NetScan. So the step 4 is how to look for code injection. Now, why code injection is in the first place? So attackers use code injection in order to camouflage, to hide behind legitimate processes, and to evade some of the antivirus and whitelisting. So I'm going to explain how a simple DLL injection works. So step 1 is open process. So what you do is you first identify the target process. This is the process where the attacker wants to inject the DLL into. So by opening the target process, the attacker then gains access to the memory space, right? So the second step to it is virtual allocex. So what virtual allocex does is that it tries to understand the number of bytes that are associated with the DLL file path, and then it allocates the address to the victim process, right? And then what happens is we use something known as get module handle A and get process address. So get module A, what it does, so there's a library called load library, right? Load A. So that load A has a specific address. So for the so in order to get address to that load A library, you use get proc address, get the address to load library, and then you create a remote thread. So that's like a very brief overview of how DLL injection works. And these are the modules that you would use to identify DLL injection: LDR modules, malfind, and holofind. So the most reliable plugin, in my opinion, out of the three is LDR modules, because these modules, in turn, they point you to the three linked list which I explained during the initial slides. And how do you extract the process? Now we are at a stage we have identified malicious processes, and we want to extract them out of the system for further analysis. So the way you do that is by using these plugins that you see in the slide. So I want to just quickly give a run through of the demo of how I've performed memory analysis. If I can just speed this up. So what I'm essentially trying to do over here is trying to run various plugins against the raw image of the RAM. So I'm running netscan, pslist, tree, command line, file scan, DLL list, and etc. So these are the plugins that I'm going to be running eventually, but it's taking a while because my typing speed is a bit slow. Okay. So with the interest of time, maybe I'll just give you explain what I have done. Is I've executed the plugins against the raw memory, and then what I did was I was trying to look for any C2 activity, right? So I assumed that there's an IP address that from where the C2 activity is happening, and I was trying to look for it within the process memory. Okay, and then what I did was I was examining the processes using pslist, pstree to see the various processes. So I wish I can just speed this up a bit, but okay, so I'll just give a context of what was happening. So I first identified the IP address where I was noticing some C2 activity. And then when I searched for that IP, I saw that there was one node that was spawning the command.exe. And that showed that there was a malicious process that was running against it. Right? So I'm just going to skip past this. To time. Yeah, so thank you all for listening. It was a great pleasure explaining to you all. I know that RAM forensics is an extremely wide topic, and I can keep talking on and on about it, but if you want to discuss or talk to me about this, you can please reach out to me on Twitter or LinkedIn, and we can have a conversation around this. Thank you so much.